Let's get started with today's program. The first is the tutorial by Professor Klaus Mølmer from Michel Institute. He will continue from where he left off yesterday. And today's title is What Can We Know About a Monitored Quantum System?
Thank you very much. Good morning. So yesterday I was giving a broad introduction to the field of observed quantum systems. I talked a little bit about Glauber's photo detection theory. I talked about how it mixes with the Schrödinger equation, evolution of quantum states. When we do measurements on systems, then there's a back action. And unlike what we see in most quantum physics textbooks, at least, they're not all just projections. And for Neumann's projection postulate, they can also be only slight perturbations of the quantum system we are interested in, because we're actually not measuring on an atom, we are measuring the light that leaves the atom. And it may carry only a faint trace of what is the state of the atom. And therefore, the back action is also going to be only a gentle change of the quantum state. So I showed you the quantum jump dynamics, which is actually more radical. The atom does go to the ground state when you observe a photon coming from that atom. A little bit the opposite, actually very much the opposite of Bohr's model, who says that the atom has the electron going down to a lower orbit, and then of course there's a photon emitted. So that was a physical model where there's physics going on in the atom that leads to the emission of the photon. In quantum mechanics, the Schrödinger equation is continuous, but there's a discontinuous element in the measurement process. And that is how the quantum jumps now become the consequence of seeing the photon, not what triggers the emission of the photon. But it's the same physics, so delightful to be at the Niels Bohr Institute where the quantum jumps were introduced, and now having another argument for why these quantum jumps occur in the formalism. I was running through lots of different things, and I ended up talking also about some retrodiction work that we have been doing. And what I'm going to do today is actually take up and go through a number of examples of quantum systems who are subject to measurement, and some of the many wonderful effects and useful effects you get out of looking at quantum systems. We can, of course, learn about their dynamics, we can verify quantum mechanical predictions, but we can also use the measurement process as an engineering tool in designing quantum states and getting states that we like. And I just talk about a number of these examples and a number of different systems, and maybe also try to indicate how the formalism can be gradually adapted. Yesterday, Abhishek gave a nice talk about many-body systems being monitored. And of course, we also monitor sometimes many-body systems, and the idea of the trajectories is the same, but the tools may sometimes have to differ because we don't have a Schrödinger wave function for a many-body system, but some other effective description of the quantum system. And that is something we can also do and develop. Thursday, oh, that's wrong spelling up here. Thursday, it's almost like in Danish now, but there's an H missing. Quantum trajectories, I'll talk about what we can learn with a monitored quantum system. And by that, I mean using a quantum system as a sensor for something which is potentially classical. So you can have a magnetic field sensor based on atoms, and you will read out the state of the atom. And that's going to be the same stochastic process as if there was no magnetic field around. But the measurement record will now tell you the strength or direction or properties of this magnetic field, acceleration of your system, or whatever quantity you're interested in. And that connects closely to Felix's talk yesterday, of course, which was about sensing with trajectories, and I'll just give a whole lecture on that topic Thursday. So I showed this drawing also yesterday. It's from a Zurich article about the paradoxes in quantum physics or interpretations of quantum physics. We live in the classical world, but we have some control over quantum systems, which are here visualized as something living in a quantum world. Actually, Bohr never referred to a concept of a quantum world. He says there's only one world, there's a classical world, and then we observe phenomena that needs a quantum description. But that doesn't mean they live in a quantum world. But anyway, this distinction between then phenomena that have to be described by quantum formalism and phenomena that can be described by classical formalism exists. And I can drive a laser completely classically, turn it on, shine it onto atoms, and if I want to know what happens with the atoms, I have to use the Schrödinger equation. And then I can get photons out, fluorescent photons from the same atom, and then I detect them on my classical detector, and I listen to it, it says click, I know that something has happened, and then there's an evolution of the quantum state, the wave function, which is the quantum jump or some other dynamics happening in the formalism describing this atom. And this is measurement here on a single quantum system. There is this collapse or back action or state reduction accompanying the measurement you do. And this is not the same as Schrödinger dynamics. It's non-unitary, it's not linear, it's non-local. The measurement here has consequences on the state over there. And a lot of discussions, of course, between Bauer, Einstein, Schrödinger, about the description of this and being very paradoxical and how should we interpret this theory took place. Alongside with all the physicists who practice quantum mechanics to solve physics problems, the shut up and calculate group who are just using the formalism. And what I would like to claim is that now with the trajectory theory, we can also shut up and calculate and now describe these phenomena, right? Because now we also have a formalism that describes dynamics conditioned on measurement. So this is just as having a formalism that allows us to calculate these things. And we don't have to sit and do philosophical discussions about this atom does. I can use quantum trajectories or Monte Carlo wave functions or what you call them to calculate quantitative properties of the system. And I can simulate measurement records and I can interpret what is going on with a formalism. So that's a good fact about having a measurement theory. It's not a part of a debate, it's also just a numerical tool. And then that's how it is largely being used, of course. And I will not say so much about the history because I saw in Howard's abstract that you, Howard, will talk about some of the history of this. So, but at least I have to acknowledge that, of course, I'll talk about things that we did, but there was actually a lot of activities going on at the same time. So Gerd Hegerfeld and Plenio and Göttingen were doing some work. I'll just show you one picture of what they did. Howard Carmichael did wonderful work. We did our work. Weismann and Milburn did things, and there are differences between our motivations. I think in the very early Weismann-Milburn work, there was the idea to use the measurement record actively to apply feedback on the system, to use the knowledge you get to immediately control the system dynamics, which was in none of these other works, for example. And then, of course, we also, to our pleasure, we realized that, wow, there's actually been a lot of activities in this field prior to our work. I think even in the late 70s, Belavkin has his first paper, and there was Slava Belavkin, Bakeli, Diorsi, Chichin, Percival, and on the more philosophical side, Girardi, Rimini, and Weber, who were all looking into this stochastic approaches and different purpose, but it turned out to be the same equations. Right? So it was very interesting, a lot to be learned from that. That's what I would say about the history, apart from just one slide where I will show what was driving those two projects here. So here is a slide where Carmichael wrote a book instead of 10 Fistweb letters about it. And so this is a wonderful Springer lecture note. He gave a course in Brussels, and that course he was developing this whole theory. And then he published this lecture note, and which came out from Springer. And his purpose was to understand the structure of the detecting signal. How can the signal fluctuate the way it does? And you cannot make a simple classical machine who makes that signal come out. It's not a classical field will not be these fluctuations. There was this long debate whether light is quantum or not, and it was largely based on the correlations, the fluctuations you see in the signal. Can they be described by a classical theory of a fluctuating magnitude or amplitude of the field, or does it have to have a quantum description? And instead of being philosophical, Carmichael actually just wanted to be able to have a theory that can predict anti-bunching character, the click records looking the way they do. And he realized that you have to combine together the evolving quantum state of the emitter and the signal. So Born's rule takes you from the state to the signal probabilities, and when you have the signal, there's a back action on the quantum state. So it's also what I talked about yesterday, but where my purpose was more to understand the atomic dynamics, Carmichael's purpose was to understand how that record came about. And we had no idea about the work of the other group, right? So we made the same theory with two different purposes. And for him, the quantum trajectory is actually the pair composed of the state and the signal, because they are developed together, right? You cannot know one and not the other one. And who's the child on the picture? Well, that's my daughter, and I kept photographs of her in Howard's book because I always had the book with me for a long time, so then I would be sure always to bring the picture of her with me too. And the other work, the one by Hegerfeld, well, he was looking at a very particular phenomenon. If you take ions in an ion trap, and you can look at just a single ion, then if they have a three-level structure, as the one I show on the right, then it's going to look like this. This is 5 ions in the ion trap. This is real-time movie, actually, from an ion trap. So it looks like that. So you can see that sometimes they are on and sometimes they're turned off. Okay? And the reason is that sometimes the ion is dwelling in that state where it lives for a very long time, and other part of the time it's excited up and down on this transition, and what you see as light is the fluorescence photon coming from this decay. So you know, if you take a master equation, you try for solve for this system, you find steady state population in both of these states, and you find a prediction of reduced intensity of the fluorescence because it has only reduced population in that state because of the population sitting over there. But that's not what you see. You don't see an average reduced intensity because of this level. You see blinking because the system is actually jumping. So these are macroscopic jumps in the sense that the signal goes from 2,000 counts per second to 0 counts per second, and then sometimes later up to 2,000 counts per second in the detector. How can we understand that phenomenon? Right? Because we have a density matrix theory who does not at all show this kind of random features of on and off. And for that purpose, Higgerfeld and Plenio formulated made a formalism who could do that. And the formalism is simulating the detection of these clicks. And what turns out to happen is, of course, sometimes you just simulate many of these after each other, but sometimes the population gradually starts sneaking into this state. And that sneaking into that state is sometimes not interrupted by the next jump until it has all slipped into that state. And then you get a long period where you have this fluorescence being completely off. And then it comes back on again. So that's demonstrated beautifully by that theory. So they develop, of course, exactly the same formalism as Carmichael and our work to simulate this phenomenon. So it's kind of interesting, right, that we come with such different motivations and find this answer. Okay, so I just showed this picture to you already yesterday, saying that the way that all these derivations are essentially acknowledging that the atom with no photon present will evolve in a short time step into a superposition containing a component with a photon in it, but the atom in the ground state. And in a density matrix theory, you can think of putting on sunglasses so you're blind to the photon, then you just see atomic populations and you add up incoherently those two populations. But if you see the photons instead, and the master equation describes this density matrix, the effective description of this system. But if you instead detect the photons, you get random behavior because there's either 0 or 1 photon when you detect, and then you get the quantum jump formalism. And so that is how we got this formalism. I'll now talk more about the consequences or uses of that formalism. The Lindblad equation can be simulated by this dynamic. So if you do a large ensemble of these wave function simulations, you get on average the same as if you solve this equation on the right. Okay? And that means that you can maybe save time in some computations, certainly not in this one. This is a 2-level system. And if you have a 2-level system, then the master equation is a linear equation for 4 components. It's a 2x2 matrix. So this is a deterministic equation. That's very fast to solve. If you use wave functions, you have only 2 amplitudes. So you solve only a factor of 2. And what you get if you solve 1 is this random behavior. If you solve 100, then you get the points. And they are following very well the curve that is the master equation solution. But of course, I didn't save any time because here I have solved 200 equations instead of 4. So it's not to save time. But at that time, I was actually working on the theory of laser cooling, and we were looking at wave functions in space because it was quantum mechanical description of laser cooling. So the dimension of my Hilbert space would actually be what it takes to describe a wave function in 3-dimensional space. So we were using something like discretization in 50 grid points along X, Y, and Z axis, and the internal state of the atoms. So we would easily have 100,000 quantum states that we would expand our state on. And the density matrix would be 10 to the 10 or 10 to the 11 elements. And that would not be nice. But the single wave function would be easy, and 100 wave functions would also be okay. So therefore, we would do laser cooling by this. And now it suddenly makes numerical sense. And there are people today who use the method in simulating the performance of quantum computers, which also have large Hilbert spaces. And then you can put all the noise terms, and you don't do it by a master equation because it gets too involved, but the wave function treatment is good. You can also ask yourself, how precisely do you actually want to know this value here? Of course, there are fluctuations. If I do 100 simulations, you expect a relative error of about 10%. Okay, that can be good enough for many purposes. If you're not doing a high precision measurement and prediction of a number, if I want to know the temperature in laser cooling, yes, I want to know that it is 40 millikelvin, but is it 42 millikelvin or 38 millikelvin? That's maybe not so crucial. I just want to know that it's below 100 or below 60. So there can be many good reasons. There can also be, for some systems, like the quantum jump approach by Higgerfeld, just looking at a simple trajectory teaches you something about the dynamics. It also teaches you about the mechanisms, actually. I should just go back to that. The sudden disappearance of this signal is because there is a rather sudden collapse of all the population into the state who is shelved. How does that actually happen? That happens because the absence of photons here causes a reduction of any amplitude sitting on that state up there and a renormalization of the state. And that renormalization contributes to kicking population into that level. It's not always the Hamiltonian who drives you into a state. It can also be the absence of clicks, the part of the dynamics where you don't see anything is actually having that kind of consequences. There's something called dark states in spectroscopy, superpositions of atomic states who don't absorb light. And atoms fall into these states, but they don't necessarily fall into them by spontaneous emission, because they would typically put you into one or the other of those states. The reason you fall into these states is because you don't see photons, and you sort of renormalize population up into those states. So that is something I found was very illuminating, and I actually still learn a lot insight into physics dynamics, just seeing just what a single trajectory does, because you can see a pathway for dynamics. I said that at a talk in Munich at the Max Planck Institute once, said that you could learn something that you could not understand before, and I won't say his name, but an old professor stood up and said, that just shows how ignorant you are yourself. And I could only say yes, but it was of course right, but it was also kind of funny. Sorry? Yeah.
Can you go back to the
Yeah.
slide? Yeah. So I mean, so when it's in the what are those fluctuations? I mean, what exactly are those fluctuations?
What you see in the picture here?
Yeah.
Yes. Oh, yeah. Sorry. Thank you very much. This is the same as I showed in the movie. This is actually the detector recorded counts per millisecond on a detector. So there are many counts per millisecond, many counts per the next millisecond, and then suddenly there's a drop, and there are no counts for some time, and then it comes back again, many counts per second. And these fluctuations, they are more, I mean, they have a little bit of technical fluctuations, but of course also there will be shot noise fluctuations in how many counts you get. But the number of counts on your detector per time, and it was just a movie I showed you, so that was very bright, and then it got very dark, and then it got very bright. And it happens in the lab. I mean, I've seen it with my naked eye. You can actually see it in a dark lab, that an ion fluoresces and stops fluorescing and starts fluorescing again. You know which state it is in when it's not fluorescing. So I even got a little lamp in my hand, and then every time it got dark, then I flashed it onto it, and I drove the transition back into that state, and then immediately it started fluorescing again. So if you're not familiar with these experiments, it's actually quite a divine experience to sit alone in the lab with a single atom, and then controlling its dynamics. But it is really, here it's macroscopic. It's 100,000 clicks per second or 10,000 clicks per second. The decay rate for that upper level, or the lifetime of that level, is maybe 10, 20 nanoseconds. So it will emit millions of photons per second when you're driving this transition. And here we are counting a good fraction of them.
When it goes to that kind of the other state, then it doesn't fluorescence, but you still see some count, right? So
you see always, you mean there's a little bit of noise down here in the bottom. Exactly right.
Oh,
so yeah, so photon counters, these are avalanche photodiodes. Of course, you want them to be sensitive to single photons. So therefore, there will be a few what we call dark counts even when they're not illuminated, just because of noise. Yes. So this is the macroscopic signal, and what they really wanted to describe was, of course, how can you make these big jumps? That's a really odd thing, right? But it's really due to the system either doing this stuff or sitting up here. This is how we today read out ions in ion trap quantum computers, actually. So very nice, very well motivated for many different reasons. This method came into use. We were looking very much in the beginning of on dissipation. So I mean, there's going to be emission because of spontaneous decay of the atom. And it is that emission that we are detecting. And from general master equation, all these different damping terms, we pretend that we monitor them. And that means that instead of having them sit in the master equation as damping terms, they now become stochastic terms where we do something on the atom because we pretend to actually measure something. We always call it gedanken measurement because with Jean and vivant, we didn't think that this was a theory about measurements. We thought this was a way to simulate dissipative dynamics. Right? But of course, it's both. So we measure the emission decay here. There's also another school of thought, and I think maybe Howard Wiseman and Milburn were the first one to turn it into that perspective, and that is that you can think about it as probing the system. So of course you are probing a system if you're driving it, monitoring its emission, and you learn something about the system from that. And there's also other kinds of probing. You can also probe, for example, a gas of atoms by sending light through it, and then look what happens to the probe beam. Does it change its phase? Is it depleted because of the absorption in this medium? So that's another probing situation. And here that the system may absorb some light, it may phase shift the light, it may emit some light because of the excitation of the system. But if you put the detector here, you're going to detect those two signals together. And I think the philosophy would often be that, well, it is actually the phase shift of this field, or it's the absorption or depletion of this intensity that you're actually probing. So in classical optics, there's something called the Ewald extinction theorem, who actually tells you that the field anywhere in space is the original beam plus what is emitted by the objects that it encounters on the way. And that's, of course, exactly what we are measuring here. We're measuring the interference, or at least the sum of those two signals here. And in quantum optics, there's a thing called input-output theory, who tells how this output field is the same as the input field, plus what the source here is actually doing to the field. And in probing experiments, that is what you are interested in, right? Then you can use light to measure the thickness of a piece of glass because of the phase shift when you go through the glass, or you can measure the number of atoms if it's atoms who cause the phase shift of the light. And this is done in many, many experiments. So this also will take a slightly different form, because if you're measuring the interference between the emitted signal and the original beam, it's a bit like the homodyne detection I described yesterday, because this acts as a strong field that interferes with the signal from this sky itself. So this becomes typically the quantum diffusion type dynamics, because you already have the strong beam sitting, and then you see this extra field in the presence of that one. I understood that Pierre gave talks about this last week, and he has a very nice review paper, which is probably also appeared, but I give you here the archive reference to this paper. And of course, all the papers that you find in the literature about this will also develop this theory. Now, I also described what the quantum trajectory is in some sense. I said if you have an initial state and you think about a completely general measurement on the system, could be one of these probing measurements, or it could be photon count measurements, then depending on the outcome of the state, there is a certain recipe. What is the operator that you should apply to psi? This could be the quantum jump on the state. It could also be the absence of a jump, which is also corresponding to a certain final state. And the probability is given by this expression. If you then do a second measurement, then you act with the second operator on the state you have now. So you get M2 acting on M1 acting on psi, and the joint probability for these two things is going to be the norm of that state. And you can go on, and this is then actually the trajectory, because the state changes all the time. There is generally more things happen to the state than just measurements. I should generally also put the time evolution due to the Hamiltonian here. And if you go to the mixed state density matrix description, I should also put all the Lindblad terms that you don't observe here. But I mean, just for simplicity, I show you this clean case of doing only measurements on the system. And this is really the trajectory where I know what is the density matrix at any time. And there's a joint probability for getting all the measurement outcomes that I just wrote. And if you do a final one that I label by another symbol, omega instead of m, then the probability to get outcome k for that one is also just to be inserted in this formula. So you have a joint probability for these guys, which is just given by this norm of that state. And since you already know the initial ones, it's not a probability distribution for them because they already happened. So this is actually going to be the relative probabilities for the different outcomes when you are at the time where you do that last measurement. And that's not so surprising, because this whole composition up until the omega here is the state at that time. So with that being the state at that time, is just the normal rule, the same as I applied up here, just applied to this operator with a different wave function. So that is how the trajectories work, and how you can think about the state evolving, and how you can now make the prediction for the next state using Born's rule and this more general theory. So here are some examples of doing that. First, at some discrete case examples. So this is a beautiful thing also to show you the usefulness of measurements. So the figure is a little bit odd. Well, I can't say that about a nice paper by good colleagues, but it illustrates two atoms, one located here and one located there. And these atoms can emit photons in spontaneous decay. And initially, they are both in the excited state. So these photons are allowed to escape from the atom here and escape from the atom there. Then they are combined on this beam splitter, such that the light that goes down this side is a superposition of photons coming from left and right. And this one is the other superposition, the one with a minus sign, from light coming from left and right. So if you have a click in this detector, you don't know if the photon came from the left or right atom. Actually, it came as a superposition from left and right atom. And the quantum jump will take you into the application of a superposition of this jump operator and that jump operator on the excited state. And this is this state. So this is an entangled state. These are atoms who could be kilometers apart. These could be optical fibers. They have never interacted with each other. They have prepared classically, locally in their excited state. And one measurement process puts them in an entangled state, which could then be used for Bell test and funky things. So it's a wonderful tool to establish the state that we really like to display non-local correlations quantum mechanically. And it's the measurement who did it. It's very difficult to do such things by Hamiltonians because there's no interaction between atoms so far apart, but it's very easy to do by measurement. And there are experiments doing that. So Chris Monroe is operating ion traps, and he's operating pairs of ion traps, and he takes photons from those ion traps, and he generates and he validates that his ions actually now come into entangled states in those two traps. Right? So that is a way, in the long run, to enable communication between different quantum computers and build internets of quantum computers. So very useful. This is a more complicated experiment, and I have to explain the figure also. What is sitting here is a gas of atoms. And the atoms, there are many atoms here, there are 10 to the 12 atoms in this experiment by Eugene Polsik. And these atoms can be in two different hyperfine ground states. And by sending light through, you're probing whether you are in one or the other state. Okay. But the interaction is very weak. So what is actually happening is you get a small phase shift per atom in one state that you don't get if the atom is in the other state. So the total phase shift of light going through this gas is proportional to how many atoms are in that particular state. Then you can go through another gas where you have exactly the same interaction. So when you probe this phase shift by homodyne detection in the end, you have measured the sum of how many atoms were in that state in those two gases. So you actually not measured a local observable, you have measured the sum of a collective spin component here and a collective spin component there. And the result is an entangled state, because it's the same as angular momentum theory. You know, the states which have a total angular momentum, they are superpositions of different product states of the two smaller angular momentum systems by Clebsch-Gordan coefficients. So this is a way to entangle macroscopic systems. And of course, Eugene has written many, many papers demonstrating teleportation between such gases, transfer of quantum information between them, and many, many other protocols. Establishing the entanglement by a pure measurement process, and then doing the dynamics you want to do. Validating it, of course, by similar measurement processes in the end. So measurements are a wonderful resource. And I should say that this is an experiment where I've been working on this myself. You actually have to apply a kind of trajectory theory here, because it's not an instantaneous snap measurement like up here. Here you integrate over time. And the more photons you scatter, the more precisely can you measure that phase shift. And the more do you actually resolve this total number of atoms added together in these two gases. So it's not happened at an instantaneous measurement, but as a consequence of probing over time the stochastic signal that you get here. So it's really a trajectory theory, if you like. Okay, there's also another application of measurement in connection with cavity QED, and we have looked at it and others have looked at it too. Cavity QED is often shown with this example, with a two-level system sitting inside a cavity, resonantly exchanging energy with the cavity mode. So the excited atom can go to the ground state and add a photon to the field, and it can reabsorb the photon again and go back to the excited state. This is in competition. This happens with a strength G or frequency G, but it's in competition, of course, with the loss rate of the atom out of the cavity or of the photons out of the cavity with rates gamma and kappa. So if you want to see this phenomenon, your G should be larger than gamma and larger than kappa. So you see the oscillations before they decay. And this parameter, the cooperativity parameter, G squared over kappa gamma, tells whether you will be in such a regime or not. Now, there have been proposals to use a cavity to entangle two remote atoms. And you can see the idea could be very simple. The first atom emits into a superposition a photon and it's now back in the ground state, or it stays in the excited state and there's no photon. And that field is now observed by the second atom, who can absorb the single photon component and itself become excited. So you get a superposition of excited ground and ground excited of those two atoms. That's an entangled state enabled by that physical process. And when you calculate the fidelity, how good can you make that state? Of course, because of the losses, it will not be unit fidelity, because there will also be a chance you lose the photon. And if you do it the best we can do using the Hamiltonian, you get a fidelity which is 1 minus 1 over square root of this C number here. So this C is often around 100 in cavities, and then you're going to get a 90% fidelity of this operation. But you can also trade success probability for fidelity. So you can also make a measurement signal out here. And then you can probe on this field. And we have a particular protocol which is not exactly what I just explained to you, but you're sitting measuring by homodyne detection a field coming out here. And then you will find out that with a high probability, which is roughly the 90%, you will have a higher fidelity closer to 1. So I can make the system not deterministic, only almost deterministic, but benefit in the fact that the state I get in the good cases is a much better one. And that's also a kind of trajectory theory, right? Because you have to sit and monitor, and sometimes the heralding that it's a good state will be based on a measurement record over time, and therefore we have to use this the trajectory theory to actually analyze whether this is working or not. So, and this is not an authoritative paper on it, but this is something I did with a super talented now colleague at the Bauer Institute. Here's a many-body system that we looked at. This is a Bose-Einstein condensate. So this is a really many atoms. And if you ever saw the pictures of Bose-Einstein condensates, many of them were made in the following way, that you shine light on the condensate from the left. You don't want the condensate to absorb the photons, because the photons have energy and they have momentum. And then you will heat up the Bose-Einstein condensate. So what you do instead is you go off resonance. So the laser field will experience a phase shift when it passes by the atoms. And the phase shift will be proportional to how many atoms there are. So the kind of column density of atoms in this condensate will reflect in how big is the phase shift detected by these pixelized detectors I show here on the right. So that's nice. That's how they do the pictures. Now, what is the back action on the system due to these measurements? What happens to the condensate when you're probing it and you get your signals here? So one thing that is characteristic for a condensate is that it is one big macroscopic wave function. And there's actually associated with each little volume a Poisson statistics in the number of atoms in that cell. But now I learn that number better because I measure it. So that means I'm disturbing the ground state of the condensate. I'm actually exciting the condensate. And we wanted to see what kind of excitation do you put into that condensate. If it's only a weak interaction, then the excited state of the condensate are described by sound modes, vibrations of the condensate. There's something called Bogoliubov theory that gives you the equations for these modes. It's Bogoliubov kind of two wave functions, because it actually involves a kind of particle and hole theory, because you have removed particles from some place and you put them somewhere else. So it reminds a lot of what you do in solid state physics with particles and holes. But we know the spectrum of these modes, we know what they look like, and so when you shine light on it, you can study what is actually happening to those modes. So here's 3 Bogoliubov modes, which are all in their ground state when we start. And then if I'm probing and flashing the light at the frequency of one of these modes, I will actually squeeze that mode. So this is the variance of an X quadrature of these modes. They are oscillator modes, so it's just like harmonic oscillators. And this variance shown here, or noise shown here, is actually showing that you are going down because you are probing and therefore squeezing the Bogoliubov mode. And we select that one by probing at the frequency of that mode, and that will effectively squeeze that one. The other modes are completely untouched by this probing, but then if I instead probe at a sum of the frequencies of 2 modes, I start entangling those 2 modes. So actually, in this case, the first and the third sound wave in the Bose condensate, they are in an EPR entangled state, where I have squeezed the X and P quadratures, but commonly, so X1 minus X2 is squeezed, and P1 plus P2 is squeezed in this case. Okay, so this is actually a place where you could do, perhaps not a Bell test, because it's the same physical system that holds both modes, but at least you can induce quantum states of the Bose-Einstein condensate. Quantum states not in being spatial wave functions, but the number statistics, the distribution of where the particles are in the gas, has now become strongly correlated because of the probe back action on this particular system. This is, of course, in competition with, or could be done jointly with using the interaction between the atoms. but the interaction between the atoms is very local. So that would not naturally address these big extended modes of the system, while the probing is actually selective to these modes. So it's a kind of a funny thing. And the last thing I want to say about many-body physics is something that also says something fun about the signal we actually get when we do the probing. So this is another famous model with cold atoms. You have a periodic potential, and you have a lot of atoms. And then they can, of course, distribute themselves in the different potential wells. And if the atoms are non-interacting, the ground state will actually be one where all the atoms will be in the lowest block solution of this periodic potential. So this will be the Bose-Einstein condensate, where all the atoms are in the k equal to zero momentum state, which is a superposition of all the sides. So every single wave function will be located all over this lattice here. But as soon as you turn on, for example, a repulsive interaction between the atoms, then they don't like that all of them have a chance to actually be on the same side. If they are all over the place, there will be probability of having 2, 3, 4, 5 atoms on the same side, and that will be suppressed now. So this interaction term here, which is proportional to the number of atoms on the side times the number minus 1, so that's just the interaction. That is, if you have n atoms on the side, that will suppress and favor this, what's called the mod insulating phase, where there could be precisely 1 atom per side, for example. Okay. So we can have such a system. And then, of course, if you have both present, there's going to be a competition between those two. And when you have that competition, what happens if you actually start probing the system? And we can probe, for example, just a crazy operator here, we can probe what's the total population on the even sides. I don't want to probe the total population because that's the number of atoms. So that's trivially already given. But on the even sides, that will fluctuate little only if they are in the mod insulating phase, because there will be exactly 1 on every side, so there will be exactly n over 2 atoms on the even sides. So that will be a quantity that doesn't fluctuate. But if I'm in the superfluid phase, the phase where all the atoms are distributed all over the place, then this guy will not be in an eigenstate of this guy. So measuring that will excite the system and drive the system. So this probing works. And what I show you here is not, of course, it's a simulation we did, but I'm actually just showing you the measurement record. You take the measurement record, weekly probing this quantity, you have a weak homodyne signal, but it's fluctuating over time. You take the Fourier transform to see what are the noise components, and if you are in the regime of the mod insulating phase, then you have a delta function peak. So you just measure the signal, like a laser field going through. But then if you start increasing the coupling strength, this U over J here, this is the tunneling rate, then the spectrum starts developing some width, and here you even see discrete wings here, and that's because you're now probing the excitation spectrum of that Hamiltonian, because you are not measuring the Hamiltonian, you're measuring something that does not commute with the Hamiltonian. So it looks more like spectroscopy. So in fact, you can see the transition between not being noisy and being noisy is actually where you expect the phase transition in this system to occur between the superfluid phase and the mod insulating phase. So this optical probing would be a signature of the phase transition in a many-body system. And just to prove that it's right, we can also measure the coherence, which would be a Hermitian operator representing the current going between the 2 neighboring sides. And in the mod insulating phase, this vanishes because you are locked to the different sides. But in the superfluid phase, this has a finite mean value. And when you probe that, it's exactly opposite. Then in the strong mod insulating regime, you have one outcome with no noise, and in the opposite regime, you have the noisy outcome. So I like to think of this as being, of course, a nice demonstration of what the trajectories allow me to simulate, but it actually also illustrates a property of the trajectories. What you're really probing when you get a signal in a trajectory is the effect of back action of earlier measurements, right? Because they are the ones who induce dynamics in the system, which is being probed by the later measurement. And that is something they use a lot in many-body physics under the name of quenched dynamics. So if you want to know a lot about a system, you don't measure its steady-state properties. You hit it with a hammer, and then you hear it ring, right? It tells me more about a bell if I hit it with a hammer, because I can hear all the eigenfrequencies and the damping of the eigenfrequencies. So I learn about the Hamiltonian and the damping terms, but I have to excite it first. When you do the trajectories, you are at all time steps exciting it because of the measurement back action. So we are doing an automatic quenching and probing at the same time, and we can learn essentially the same as if you hit the system with a hammer. So that is kind of funny. It's also funny here that it's actually, in this case, the property are you in one quantum phase or another, the superfluid phase or the mod insulating phase? That's more a property of the Hamiltonian and the dynamics than of the state itself. So it's the response of the system. But actually, when you do this Hamiltonian and you do this probing, the steady state is going to be a very hot, almost identity density matrix. Because, I mean, that's what you get when you solve the master equation. So we're actually not particularly probing the ground state here. We're more probing the response of the system in any state to these perturbations. Okay, that's a bit technical for the many-body experts in the room. Now, this is a thing I showed yesterday, that, of course, the trajectories also work on the toy model quantum physics, also the ones we can make in the lab. So Arash is doing this beautiful experiment. I'll say a little bit more about that immediately, where he can send photons through a cavity. And in this case, if there's this number of photons in the cavity for between 1 and 8 or even further down, then the probability for the atom, to leave in the same state drops from 100% down to 4% and 0%. So if you do the statistics of the atoms coming out, you will learn which is the photon number in the cavity. So I showed you this figure also yesterday, how you start with a prior uniform distribution, and then due to the measurement record, you learn that there were 7 photons in this cavity, in this experiment. Very nice, and this is what it looks like if you show these on a graph for longer times, the jumping dynamics from 5, 4, 3, 2, down to finally 0 photons in the cavity. Now, what I really want to show you now is the use of this to control the photon number state in the cavity. So this is a lion tamer, and he now wants to tame this Arash experiment. Of course, it's not a lion tamer, but it's an extra feedback loop. So when you have detected the atom, you go back, send an instruction about the next atom you send into the cavity so that it can push the field in the direction you want. So based on the knowledge you have, you can now correct the state in the cavity. And Arash said, I want to have 4 photons in my cavity. Of course, you're not going to get 4 photons. Well, with maybe a probability of 1 in 8, you will get 4 photons. But if you get something else, you can correct for it. So here he starts measuring, and the photon number is well below 4. But then he's just putting some so-called emitter atoms into the cavity. So based on his measurement, he says, I need to add more photons. These are photons excited and on resonance with the cavity. So when they enter, there has a big chance that they will give their energy to the cavity. And then there will be 1 more photon in the cavity. And he keeps probing. So he also measures when it comes out, if it worked or not. And then eventually, and this is the actual statistics of being in the same or the opposite state. And there was far too little in this other state to confirm the 4-photon hypothesis. That's why he entered these emitter atoms. So it's an automatic loop. Then it goes very well for some time. There's roughly the same numbers of atoms in and out, and it should be roughly 50-50 for 4 photons in the cavity. But then it gets bad again, and then you immediately put another emitter. Then it gets too much up here. Then you put some absorber atoms, so they are injected in the ground state, resonant, and then they can absorb photons. So this is a complete servo loop, and what you see down here is the probability of having these different photon numbers in the cavity being now stable around 4. And of course, this can go on forever now. So the loss out of the cavity will be compensated by these emitter atoms injected into the cavity. So this shows the potential, which has of course been developed and explored much more in many other systems, and more interesting systems. Here is 2 other experiments with superconducting qubits. One where you take, it's a 2-level system in a cavity, but of course it looks different when it's a superconducting qubit in the figure. But we were doing the same thing. You're looking now here at light coming out of that by homodyne detection. And if the homodyne detection is indicating that the trajectory is now leaning downwards, then you can just apply classical field to drive the qubit back up again. You know what is its state, so of course you also know how to rotate it back to the initial state. So in this experiment, you can probe continuously the leakage, the decay of the system, and then you can compensate for the decay simply by re-exciting it with a classical field that is needed. And it works because the measurement keeps the state a pure one, so you can just rotate it back. So here's an extension of the lifetime of a qubit by orders of magnitude. You can also ask the system to do Rabi oscillations, and then you can monitor whether these Rabi oscillations are going on. And normally they will of course be damped on a short time scale, but doing the measurement, you can see, are you the right place where you should be according to what I want you to do? If not, I'll give you a little extra notch, and then you go back again. And then you have this state forever. So there are many things you can do, and so what can you teach your ICTS, or what can you teach your single quantum system? Well, you can prepare the non-classical states that I showed you. You can control the dynamics, for example, in connection with quantum gates. Teleportation, the protocol for quantum teleportation is by and large a scheme where you apply measurement and feedback. Because you do entanglement generation, then you do a measurement of the incoming unknown state, and then there's a state reduction taking place, which makes the other particle go into a state that depends on that initial state over here. And then there's a feedback step, because depending on the outcome of your measurement, you have to do something in the end. So that's also very much along these lines. Of course, I'm not saying that trajectory people invented teleportation, but it's just, if you would ever think about doing a continuous mode teleportation type scheme, then it would be the trajectory theory we're talking about. Quantum error correction is monitoring and feedback. So again, it's a quantum mechanical process. When you do quantum error correction, you measure the state of your quantum computer. And of course, this is a trajectory type thing. It's a quantum state that is adapted by your measurement. In all current proposals for quantum error correction, you do projective measurement. I don't see any reason why you should not do weak continuous measurement and start reacting on the error when you suspect it's starting to happen, instead of waiting until you're sure it happened. When I ride my bicycle, sometimes if it's very slippery, I may fall. But if I start falling, I try to correct before I'm lying down, before the projective measurement. I said, yes, Klaus, you are now on the floor. So anyway, but of course it's not easy, because that's already a complicated scientific field. Adaptive measurements. There are so many things you can do. You can do the next measurement of another observable if that will teach you more based on what the previous outcome was. So wonderful, many things you can do. And so it's a very open research field also. Now, then finally, I'll come to this part with the past quantum state that I also talked about yesterday, but give a little bit more basis, the derivation of the formula I talked about yesterday, and then some examples of what we can do with it. So I have a density matrix conditioned on the record, and the question I did ask myself for a long time, and I also asked you yesterday, was what about these later measurements? Of course, they tell me what is the density matrix at any later time, but does this information also tell me something about the system at the earlier time? So what can it tell me about the system? So we wrote a paper, and there are other papers phrasing different questions about what you can learn about the past. But here I'll tell you, this particular thing that we are asking about. So what we're asking about, sorry, I just tell you with words now. We decided to say, let me use this measurement record to tell me what you would have gotten if you did a measurement here of any observable. So we have already such a Born rule. If I know rho, I can tell you the probability for the outcome of any measurement you do right here by the normal Born rule. So I want to extend the Born rule so that I have the same information, but now conditioned on earlier measurement and later measurement. So I can make better predictions, right? Or the stronger predictions, perhaps. And then we can, of course, use it in the sense that we can test it. We can ask somebody to sneak into the lab and do measurement here, not tell us what they got. And then I can, at the end of the day, I can go back and tell better what he got or she got than I could if I used only this row sitting there. So that is the philosophy. And it's a little bit, of course, a Copenhagen interpretation philosophy, who also says that everything we actually really want to talk about is what happens in the lab. What are the probabilities for these outcomes? Exactly. So I know the measurement record all the way. And then I'm going to ask, what does this full record tell me about the system at any moment in between? And of course, normal articles you read in quantum optics, they will very often show you the time-dependent knowledge you have about the system, but it will only be typically based on the information you would have at that time. But of course, when I publish the paper, I also know this part of the data record. So at the moment of publication, I could also infer my knowledge about the system at time little t, which is coming from measurement I did on the system later on. So I'm sure in the literature of history and archaeology, they completely accept papers where everything you tell about the past is based on something you measured after that time. So because that's what archaeologists do, right? So I go back to the formula I showed you before. I'm a little bit fast here. If I have a sequence of measurements, this is the quantum trajectory. And the joint probability of all these outcomes is the norm of that state. So what if I want to know the conditional probability of something happening here after that measurement? Well, then I have this state I already talked about before. What if that measurement was taking place in the middle of a record? Well, then I just have to put the operator there. And this will still be the joint probability for all these measurements, including the unknown measurement here, and then the rest of the guys sitting there. Right? Because that's the probability of getting whatever you saw, whatever my best friend saw, and whatever I saw after him. It's all a sequence of measurement, and this test measurement is just part of that sequence, which is now sitting in the middle. So I call it omega just so we can get a symbol that it doesn't look like all the m's, and then I will have that the joint probability for all the events is the initial state acted upon by all these POVM operators, including these unknown ones, and then including all the ones coming after it. And this is a joint probability for all these outcomes, but since the black ones are known, it becomes actually only a function of k. And that is the relative probability for this having happened at that time. So, wow, it was not even difficult. This is the formula for the past probabilities for this of having happened. But I still want to show you a slightly more involved equation for it, but which is actually a little bit easier to work with. And that's a little bit surprising, but it turns out that this is easier to work with density matrices, although this is already pretty nice. So yeah, let me just flesh out here again. This state up until this point is the state evolved until that time. This thing afterward is not a state, it's an operator here sitting here, but it's an operator who represents the kind of hindsight information you get from these later measurements. It's the collective or the total measurement effect of all these measurements. It's itself a POVM, which just has many outcomes as the parameter telling what it is. So this is the formula, and I want to write it in a different way. I want to do it for density matrices, so I start with an initial mixed state. And then when your measured outcome is little m1, the action on the state is to act with m1 from the left and m1 dagger from the right. It's like coming with the projection operators from both sides on a density matrix. And the probability is the trace of that object. So it's very similar to the wave function description. And if you do many measurements, then you just have to come with the M2, M3, M4, and the daggered ones on the right. And at some point you come with this omega that we don't know from the left and omega dagger from the right, and then you keep going, and here I draw them in purple, the later measurements than this omega. And this is the probability for having all those measurements. And since the black ones and the purple ones are already known, it becomes the relative probability for the middle measurement, the unknown measurement sitting here. And I call it conditional because it's conditioned on the other ones. I write not equal to because this one is not normalized. So the only thing you need to do is actually to calculate all of them for all m's and divide by the sum. So that's the normalization of this function. That's normal. That's the same also with classical conditional probabilities. Now, this expression is the expression for that probability. It still doesn't look very nice. I don't know if you think it looks nicer now. What I have done is I have taken this M operator, and because this is a trace, I can move it to the other end of the product. And I can do that with all the purple M's. So that now I have the omega as the left one, then I have this early measurement thing, I have omega dagger, and then I have all the later measurement put together. And what you see here is that you have the latest M dagger, then second latest M dagger, no, sorry, the one after the measurement, after, up until the last one, and then the last M, the second to last M, all the way down to the one right after this omega measurement. This is a nice formula. This object is the conditioned density matrix at time t. This is exactly how we defined that. So this is the state at time t. And if this guy was not there, this would be the normal formula for the probability of the omega measurement. But these guys are also sitting there. So that multiplies together to be another matrix. So this product of all these guys is a matrix. We called it E yesterday, or we called it E many years ago. And I call it E because Howard Weizmann calls it E in a paper I read about that time on weak value measurement theory. So this is a measurement effect operator, you can call it, and its formal structure is given by this. So I mean, you don't have to think about where it comes from. This is just the mathematics I derived. I need to multiply these matrices. And it accounts for the later result. In fact, you can think of it as an adjoint backwards trajectory. If I stick in the identity matrix here, you can see there's a kind of evolution of that matrix starting being the identity, then it's multiplied left and right by M dagger and M, and then it's multiplied by the M dagger and M from the slightly earlier measurement, slightly earlier, slightly earlier. That's exactly opposite to rho, who is getting first measurement, later measurement, later measurement. This one is going from the latest to the earlier measurements. And it has the daggers on the left, so that's why I write adjoint here. So we actually solve equations for rho and E who are similar, but not the same because of this adjoint thing sitting if there's a quantum jump happening in rho going into the ground state, this operator will take you into the excited state of E, but E is not a state. E is just a matrix. And the probability for the M outcome is just a formula that you see here. It's just more compactly written: trace omega rho omega E, where rho of T and E of T are these two matrices that you get in this particular, with this recipe. So here's a drawing for those who don't like the equation. So this is two physicists. One has a state that he has meticulously measured, so he knows what it is, at least in the form of a density matrix. He lends it to a colleague, said, play with it if you like, but give it back to me afterwards. And no matter what this gentleman does, no matter which observable he looks at, the probability for the distribution for the outcome of the measurement is given by this Born rule. So Niels Bohr here can actually tell what Einstein is going to get, at least if Einstein tells him what property he's going to measure, or he can give probabilities. But then Einstein gives the system back to Niels Bohr, and Niels Bohr starts measuring again. And after these extra measurements, this is the formula, the one I showed you before with the normalization factor for the outcome of the measurement that Einstein actually performed. So that's the formula I just showed to you. And that's how we can do the game, if you want to phrase it as a game, a guessing game. So I showed you this picture yesterday, but I cannot see this picture too many times in my life. This is the what you know about the photon statistics in the cavity as function of atoms passed through. So it's what you know at this time based on the early atoms, but not based on the later ones. But of course, when they published the paper in Nature, the refereeing process was probably long enough that they had time to also analyze the later data. And if you do that, it looks like this. Okay, so this is the inferred photon number in the cavity. Or to be more precise, this is the inferred prediction of the probability that you would measure that photon number if you were to do a projective measurement of the photon number in the cavity. Okay. And it's less noisy, and the spikes are gone because these are just statistical fluctuations. You don't know if it's a statistical fluctuation until you see the signal go back and be normal again. And then you realize, well, there's even no trace of these things in this thing down here. So it's much more smooth, which also makes a connection to similar classical signal processing theories called smoothing. So it definitely, in this case, leads to a smoothing of the assignment of probabilities. This is a test that, some kind of test that the theory is even right, because here we're just saying what we believe, but is this belief true? So in the experiment, they actually added a photon in the cavity at a secret point, which was number 4000, without telling anybody. And the experimenters in the lab, they had this red curve as the density matrix assignment of what is the mean photon number in the cavity. So with a little delay, because they had to get the statistics, they actually could see there was a rise in photon number around this point. But when you apply this theory down here, you get the green curve. So the atom number 4000 is the one who ejects the photon, and you can barely see a difference between the green curve at, say, 50% probability here between 4000 and the neighboring atoms. So cool and nice. Now, let me give a few more examples. So we talked to the Roche group. We also talked to Cater Merge group at St. Louis, because Cater was working on superconducting qubits. And they are wonderful systems because they do wonderful quantum optics. And you can do readout measurement processes on them. And you can rotate them. So you can actually do all these wonderful games that you would like with the ideal toy model. And we have a number of papers. I just want to show you this one because it's kind of funny, and it also has a nice classical analogy. So I want to look at the decay of a two-level system, okay? Knowing that it is in this ground state at a definite time. So normally you would say if you have a two-level system, the probability that it decays is of course a sort of exponential curve, this black curve here. So if you know that the system is excited at time 0, the probability to be excited at later time is the black curve. But what if you measure it at this definite time and you measure that it is still excited? Well, then you can infer that it has been excited all the time. It's the same as if you have a light bulb that has a lifetime of 20 hours. Then you leave the room and you will use a probability distribution, which is the exponential. But of course, if you enter the room, the light bulb will either be on or off. And if it's on, you know that it was on all the time. On the other hand, if you find that it does not work anymore, the light bulb, then what is the probability that it was working at earlier times? And of course, you're not going to discontinuously jump up and say, well, a microsecond before it was probably working with 40% probability, but now it doesn't. So this black curve or blue curve here is a completely classical reasoning about this probability of the light bulb functioning, given that it worked here and did not work there. And the same is true for the qubit. It's exactly the same story. So you can go in and check if your qubit had that excitation probability, if you are sure that it was in the ground state here. And you can do it much more generally, of course. So you can monitor the system during this process. So you can do homodyne detection, which will tell you something about the quantum state conditionally on the measurement. So now you're not using the exponential curve, which is for the person who don't look at the system. Now you'll get a trajectory between this point and that point. But what will that trajectory look like if you know it to be in a certain initial and a certain final state? Then you are in this row E business again. So the experiment is preparing the qubit, and it's not only preparing it in the excited or ground state, you can actually rotate the qubit into any direction on the Bloch sphere initially, and you can, that's a preparation, sorry, and then you can post-select on any direction on the Bloch sphere. And then you can ask, what was the homodyne detection record looking like in between those two events? So the scheme here is that you can rotate the qubit into the direction you like, you start probing, and then after that, well, you cannot measure in any direction, but you can rotate and measure along the C direction. So that's effectively the same as measuring that the qubit was in a certain angular direction, theta here. And then we are asking, what does this trajectory look like, and what do I know about the system at any moment in time along this trajectory? So I'm not going to go in detail, but I want to show you one particular feature of this analysis. So here is the prepared state, and here is maybe the final state. Here is the noisy record. The color coding shows where we are in time. So it changes time changes color according to time. And here's a bunch of such trajectories depending on what this random record actually look like. And there's a beautiful phenomenon that I learned from Pierre Rochon and his group that is actually deterministic when you cross these particular lines here. You can see you're red in this upper area, and then you're green in this area, and blue in this, and purple in the last one. But within those areas, you are zigzagging around. So that's a nice property. This is an analytical curve that you actually have departing at different times, which volumes or areas you will be inside on the Bloch sphere. And in this case, in this picture, which is a Bloch sphere picture, the set value is showing you actually effectively the probabilities to be in one minus the other state. Okay, so that's a projective measurement. The X value on the Bloch sphere shows you the probability of being detected in the plus X eigenstate or the minus spin X eigenstate of the qubit. The Bloch sphere is very illustrative. If you take any direction here, it's the spin projection along those directions whose probabilities are indicated by the Bloch vector. Now, we do it again. And here there's again a lot of trajectories, and the black one is just a particular one. And here's a black one, which is a particular one for an experiment where we post-select actually on being not in the down state, but being in the plus X state. So that, you might say, that's a crazy thing, but you can do it right in the experiment. So the E matrix, which is going to also be a 2x2 matrix, can also be represented in this plot because any 2x2 matrix has this Bloch vector representation. And the E starts here because that's the plus X state. Then it does something, and I warn you, this is not a state. This is just a representation of a 2x2 matrix you see here. But now I'm going to combine those two matrices into making predictions. And in this plot, it is the combination of the two, shown in the way that the vertical coordinate gives me the probability to be in the initial 0 state or the final ground state, while the X coordinate tells you the probability, if you do the measurement of the X direction, to be in the plus state and minus state. Any other direction is meaningless in this plot. This is only talking in this plot about the X outcome probability or the Z outcome probability. Okay, but since you know both, you can plot it as a point in 2D. And what is remarkable about this plot is that here and here you are outside of the sphere. That's something that you would never be with a quantum state. It actually says that I'm certain that if I measure Z, I will be in the ground state. But I'm also certain that if I measure X, I'll be in the plus eigenstate. The reason is, of course, that the rho, due to the decay, is absolutely certain that you have fallen to the ground state. But the post-selected fact that you measure the X plus right after that means you cannot measure anything else but plus if you do a measurement slightly before that. Because then it would be impossible to have the final event confirm that value. So this is a place where I know both the Z and the X coordinate of the spin at the same time. And that's why I'm outside of the sphere, but actually in the corner of this block box, as we call it for fun up here. So that's fun, and this of course we have experimental data and confirming that these probabilities are what we see in the experiment. So that's kind of funny. Now, what can you do with the past quantum state? Okay, so is it only a guessing game? Is it only about guessing something and then validating that this is true? It's kind of consistency, but you could maybe just as well say, I have three measurements in mind: the pre-measurement, the middle measurement, the last measurement. And if I read the story forward, it's also the last measurement being conditioned on the first two. Then it's normal quantum mechanics again. So let me give you examples of applications. So one is when you do probing, you are learning something about the system. And if you have a system, for example, with a large distribution, unknown distribution in some variable, if you measure it, not projectively, but just with some precision, then you will squeeze that distribution to become more narrow. So you can actually squeeze by measurement. And that's what Eugene Polsik did in the gas experiments I showed before. So let's play a game first with the spin to illustrate what I'm talking about. I have a quantum state of a spin. If I measure the spin projection along some direction, then, for example, the vertical direction, I'm in an eigenstate. That is an eigenstate of the spin. It's also a squeezed state of that spin component, because now it has a definite value, and it didn't have a definite value before. And I confirm it by the next measurement, which is giving me exactly the same outcome. So if you have a squeeze state, you can make a better prediction than if you don't have a squeeze state. And of course, this is natural. This is exactly what we're talking about. This is actually the projection postulate, because to ensure this result, the state better had to go into this A state. That is why this works. But it also works the other way. So if I don't know about the earlier measurement, I know the later measurement was a certain outcome A, then what could be the outcome of the first measurement? It has to be the same, because I cannot get any other value here and then immediately after that get another eigenvalue. So of course the retrodiction is in some sense trivial in this simple example. And now I'm going to turn to the case where I'm squeezing a distribution, not projecting it into an eigenstate, but just squeezing. Because then my postulate would be that my quantum state may be a wave function in x. If I probe the x, the state will be progressively more and more squeezed. So I get an x squeezed state at any moment in time, for example, time t. And then if I keep probing, of course, the state continues being more and more squeezed when I go down here, because I learn more and more about this x value. My measurement gets more and more precise, and I know more and more precisely where we are. But that's not really what interests me. What interests me is how much squeezed is my information about the system at the middle time due to the later measurement. That could be useful, because it could be at that time that the system was subject to some perturbation that I want to measure. And that would maybe be a good idea to do that with a squeeze state, because they're more sensitive to perturbation. So here's the data from experiments done at the Fudan University in Shanghai, where Yan-Hong Xiao and her group start with an initial state, and then as time progresses, they are squeezing. And I have to tell you precisely what is shown in this graph. Due to the earlier measurement, you can make a prediction for what will be the next measurement. You know the mean value of the quantity based on your measurement, and you will guess that that's the next measurement outcome. But because of the width of the wave function, there's going to be a probability that the actual outcome scatters around that value. And you do the experiment many times, and you measure what is the deviation from the measurement from your prediction. Okay? And you can characterize the variance of that distribution. And that is what is plotted here. That's the y-axis. So the variance is shrinking here because you squeeze the system. So you can make better predictions about the next measurement based on the earlier ones. The error bar on this plot is the error bar on the error bar on the variance, the statistical error bar. But the important thing is here that you see that on average you get better and better at predicting the outcome because the state gets squeezed. So that's no wonder. The Born rule is working with a tighter probability distribution, and therefore, of course, your guesses get better. Then it gets worse again. But the reason is experimental. In the lab, there's spontaneous emission processes and decoherences process going on. The physical state is actually literally broadening again in the lab. And because of that broadening, of course, you cannot make better predictions. Your errors will grow again. You will still guess the right mean value, but the fluctuations around that will be larger. And that's exactly this rise you see here. So instead of using later measurements to predict what happens right after those later measurements, we instead go in and say, how do these later measurements inform us about the value at the earlier point? And that will, of course, also be a prediction. Now the prediction for what you should measure should be the mean value inferred from all the measurements up to this time, and I'm going to now use them to not tell the next measurement, but a particular earlier one. And the story is as simple as before. You use the formula I just described to you to retrodict what you measured at that time, and then you compare what you actually got at that time with my retrodiction. You take the distance squared, and you take the average of that. And then you get the red points. So what is happening? And the red points start at the time t. So this is as function of this later moment down here. So you can see you start being able to guess the value that you just had. That's the same one, so that's not so surprising. It's the same point more or less here and here. But then as you keep probing down here, your estimate of the earlier state goes better and better and better. It doesn't harm you that the state gets broader. It makes it difficult to predict the future measurement, but it doesn't make it difficult to retrodict the past measurements. At some point, it doesn't improve anymore, but that's because these measurements are completely uncorrelated from what you had at the earlier time. So then there's no gain anymore. You can see there's even first it's a super good slope, the same as up here, but then the slope changes because you are not learning as much anymore. So this is experimental proof that we actually know outcome of this measurement better, 2 dB better than you do in the normal state here. So that's, of course, a nice experimental verification. The same paper included an attempt to also estimate a small magnetic field fluctuation, so we also demonstrated that you can also use this for sensing. But on Thursday, I'll show more recent sensing experiments with Jan Hong's group, where we really use this and benefit from that. The later probing is actually more efficient than the earlier one in terms of giving squeezing. The reason is that the earlier squeezing by measurement is accompanied by heating due to this decoherence processes, while the later measurement also cause heating, but they don't heat in the past. They're going to heat into their future. So that's not harming our conditional state. So this is a plot where the color code who shows as function of the later time and the earlier time, how good is the squeezing. And it's biased towards larger later times compared to the earlier time. So kind of funny. Now, I'd also like to say a little bit about past quantum states, and not interpretation of quantum mechanics, but maybe rather, it's not any particular school we are challenging or talking about here, but maybe rather some popular views you can form about the nature of quantum states that maybe you have to revise them a little bit. So I'll just give you 2 examples. Heisenberg's uncertainty relation is strictly a relation about how well we can predict the outcomes of measurements of X, and how well we can predict the outcomes of measurements of P, and those 2 variances multiplied together is larger than h bar squared over 4. But it is often described as if quantum states have a sort of internal spread in X or spread in P, that it's not possible for a particle to have a better localized X value, whatever that means, or P value, but that's not what the relation is derived to mean. It means predict the outcome of a measurement. You'll be wrong by that much. And yesterday, Howard cited Asher Paris for saying that non-observed observables have no value, right? But often we still talk about the position of a particle. But the only thing we are really talking about by the formalism is actually the outcome of the measurement of that quantity, not a value that it had before the measurement or had independently of the measurement. So we can illustrate that by the fact that these past quantum states actually literally really violate the Heisenberg uncertainty relation. And then I'll talk a little bit about a classical mixture, which was also an experiment done with Côte some years ago. So let me just remind you the Born rule leading to the Heisenberg uncertainty relation. If you have an observable A, then you know the probability that it will lead outcome little a. So this is shorthand, that you do an experiment, you get eigenvalue little a, and the probability for that is what we get from Born's rule. For example, the probability distribution to get X in a measurement of X is given by the wave function squared in that point. It's not the probability that A is equal to A. This is not the probability that the particle is an X before the measurement. It's the probability that you get X when you do the measurement. The mean value of A and the variance of A are not properties held by the system. It's the predicted mean value of the many measurements of A, the weighted mean of the little a's, with the probabilities P of A, that is mean value of A. But we talk so much about it that it becomes almost a property of the particle. But it's not really a property of the particle in any other sense than being like that. It can also be measured in other ways, and there's something called weak value measurements, and other ways that can actually sort out this quantity in a way. But I mean, they will have the same discussion. Is it a real property of the system, or where do you actually learn that thing? And the same is true for the variance of A. It's not the spread of X in the state of the system. It's the spread of the measurement values that you get when you do many measurements of the system, which is characterized by that quantity. That's how it's defined, at least in the textbooks. If you want to interpret it as anything else, then of course be free to do that. But when we calculate it, it's calculated literally as being the mean value of the measurement data and the scatter of the measurement data. Okay. The root mean square of the experimental outcome deviation from the mean is going to be the variance. So Heisenberg's uncertainty relation is about such variances. So this statement here is not about X and P being simultaneously defined. It's actually not even about X and P being simultaneously measured. This is not what we're talking about. We're talking about measuring only one of them. And we can predict that with the variance. And then we're talking about measuring only the other one. And then there's also a variance for that. And there's no quantum state that allows you to make predictions that are better than the variance fulfilling this relation. And we know why. That's Born's rule. Because if you have a wave function to give you X very well, this psi has to be a very steep rising function. But then the momentum distribution is given by the Fourier transform of that one. That's a very broad function in P space. So in fact, it's a consequence of Fourier analysis that you get this relation sitting here. And the fact that you base your predictions on a single function, psi of X. Okay, so this is nice. And with this introductory prayer to this topic, then if you actually do later measurements, then of course I'm not basing my knowledge about P necessarily on the same wave function as the knowledge of X. I can base the X prediction on the early measurement and the P prediction by the later measurements. They are independent pieces of knowledge, and therefore I can, of course, in principle also violate Heisenberg uncertainty relation. Let's do it for a spin first. And actually, I already showed you the experiment with Côte, where we knew the state of both X and Z outcomes. So there we already violated this. But let me just show it again here with a simple picture. I measure here the X coordinate. I let you measure in this time interval. And after you, I measure the Y coordinate of the spin. And now I'm going to tell you something about the outcome of your measurement. If you measured X, you got the plus direction because you measured on an eigenstate of the plus direction. So you could only get that outcome. If you measured Y, you got up because right after you, I measured Y and I got up. And therefore you have had to obtain the same result as me. So I know both the X and Y coordinates of the spin in that situation. No, Klaus, you're not allowed to say that. I know completely what is going to be the outcome of measurements of one or the other one at that moment in time. So this is violation of Heisenberg's uncertainty relation. When I realized that, I was maybe a little bit cocky and thinking, oh, now I've got to write a paper where I will write that Heisenberg was wrong. And I looked in all the literature what Heisenberg was writing about the uncertainty relation. And he was typically writing things like, this description describes the ability to make any future hypothetical measurement of a property of the system. So he is actually explicitly referring to predictions for future experiments. So of course I can't say anything about Heisenberg's claims here. Now, we are doing now instead the X measurement, like we did with Jan Hong before. And then we give you the particle, but then afterwards we measure P. Of course, I'm squeezing P into the future, but I'm also learning what is P. So in fact, if you actually did the P measurement here, I'll be better at retrodicting the value of P and predicting the value of X, and I can violate this uncertainty relation. Now, in quantum mechanics, we often illustrate X and P noises by this kind of diagram here. So along the X direction, there's an uncertainty, and along P, there's uncertainty. The area here is h bar squared over 4, or the square root of that if you show the standard deviations. The squeeze state is a state who has a narrow distribution in X and a correspondingly broad distribution in P, while the P squeeze state is the opposite direction. So you get the best of both worlds because you learn the P value from the later measurement and the X value from the earlier measurement. This figure also illustrates that if I was to measure in any other direction, I don't benefit because the initial state is very broad in the 45-degree projection. It's just down by √2 compared to the height of this thing here, right? So there's still big uncertainty. And the post-measurement is also very uncertain about the 45 degrees. So if you want to plot the probability, the error bar along different quadratures, along different combinations of X and P, you can be very squeezed in X. You can also be very squeezed in P. This is a polar plot. So the distance out to the curve shows the uncertainty of measuring that quadrature. But at 45 degrees, you have these big lobes. And the more squeezed you are, the higher are these anti-squeezed directions, and the more anti-squeezed you will be at the wrong directions. So there's a very special, it's not an uncertainty ellipse, it's an uncertainty butterfly you get when you have this retrodiction situation. This is a simple theory, just calculating these states. In the same paper, we also show how to actually get certain about all directions. That's another trick and another story. Here's an experiment, again by Jan Hong's group, where she does only the pre-measurement, and then she validates what is actually going to be the variance of measuring these quadratures in all different directions. So this is the blue curve. So she is actually squeezed in X, like we predict over here, but in P she is anti-squeezed, and then she has all these things. And you say, why doesn't it look like this ellipse? But this is not a polar plot. This is actually just showing XP coordinates. It's not in any direction, it's not meant to be the uncertainty in that direction. Here it's meant to be the direction at 120 degrees, and then actually the ellipse looks more like this funny thing here. And then when she uses also the later data for the retrodiction, the scatter around her retrodiction is quantitatively weaker, both in the X direction and in the P direction. It's not the full butterfly, but I think you can see that there are like corners here. So these are the two preferred directions, and you're not as well squeezed in the other ones. You can be a little bit squeezed in all directions. The black circle here is actually the standard Heisenberg uncertainty relation. But if you get too greedy, then you start sticking these lobes out of that circle. So that's a funny little story. Does it tell anything? Well, since it's squeezing, it's actually potentially useful for something like sensing, as I'll come back to on Thursday. Otherwise, it can become just a little confirmation. It's not like Bell's inequality that we prove some interpretation of quantum mechanics wrong here or some assumptions about the world wrong. It's more that we are demonstrating a nice effect of the quantum formalism that could maybe be a little bit surprising. It is certainly at odds with a too naive statement of what Heisenberg's uncertainty relation means. Now here's another one, and this was actually thought I had in connection with the Arroche article, and actually also a referee report on the Arroche article, namely that we do the measurement of the photon number in the cavity, and we get effectively a diagonal density matrix because we only measure the ends, and there's nothing, actually there are no initial coherences, there's nothing establishing coherences, so our density matrix is diagonal in the number state basis of photons in the cavity. This does not mean that the system is in any of these Fock states, just as much as if you have a wave function of X, it doesn't mean you are in X with that probability. This only means that if you measure n, you will get the value n with probability Pn, right? To be very careful, but very often we tend to, when we have a thing like that, to compare it to what you call a classical mixture. You say it's equivalent to if I actually had the system being in that state n with the probability Pn. And there's not even any particular disagreement, because if you assume it would be like that, then what would be the probability of measuring anything? Well, first of all, the probability of measuring n would of course just be the same. So that would be an agreement with such an interpretation. You are actually in state n with probability Pn. So what is the probability that you will find that outcome? Well, that's Pn. But what about any other observable? X. Well, think of it as a harmonic oscillator. These are oscillator eigenstate, and X is the real X quadrature. Then the probability distribution for X would be X rho X, that's the standard expression, but inserting what rho is going to be Pn, and then X overlap with n overlap with X, and that's the wave function psi n of X squared. So if you literally think I am in the state psi n with probability Pn, then the probability to measure X would also be given by this expression. Because with probability Pn, you have this X distribution for the outcomes. So this is also an agreement, potentially, with the idea that the density matrix is a classical mixture. You are in one of those states, right? And that state will then have the properties of that state, and the average will then be given by this formula. So this is why we call it classical mixtures when you diagonalize the density matrix, because in terms of this kind of prediction, it gives the same as if you actually were, by classical probability, chosen to be in one of those states. And then, of course, there's quantum mechanics who gives you the outcome probability distribution. Does this survive with a past quantum state? Well, E can be anything, very complicated, but let's be in the case where E is actually just updating our information about n. That's what happened in the Arroche experiment. We got even smarter about the value of n, right? So we learned by more precise measurement what is actually the probability you are in the end state. So this was the form of my E matrix in that case. And then the probability to be in n, the one I plotted for the Arroche experiment, was essentially the product of these coefficients and these coefficients, normalized. That's the past quantum state probability to be in the end state. And that's what I showed you. And this is literally the probability that you will measure in if you do a measurement. But is it also correct to say that it's completely equivalent to the situation where the system was in state n with that probability? That the system that I showed you was literally a Fock state with the probability given by this probability distribution. And the answer, well, we have to look at other observables, because if you only look at n, it's trivially true. That's exactly the probability you get that outcome. But if I look at the probability of x, then if there's a probability distribution for being in n at that point in time, given by this formula, then the probability to measure x would be given by this quantity. But that's not what we get with the past quantum state, because the probability of measuring x is the trace of x projection rho, x projection e. And this is the x distribution with rho, and by putting this on the right-hand side, this becomes the xex matrix element. And that's actually a formula we can also easily write down. That's the one I showed you before. That's the weighted probability distribution in x for the different n states with a Pn distribution, and this is the same quantity but now with the q's. So this is going to be the x distribution according to retrodiction. And they are different. This has wave functions to the fourth power. This is only to the second power. This has only products of Pn and Qn. This has products of different Pns and Qms in it. So we just have two different predictions. Right? And this shows to us that no, even though the retrodiction only talks about diagonal elements, there are only diagonal elements. There are no non-diagonal elements predicted by the theory. It is not the same as having been in a classical mixture of states at the earlier time. So we have experience again with Cater's group, where it was possible to prepare an initial state, which was a mixed state along the z-axis of the effective spin, the qubit spin. And it was also possible to make a measurement in the end that was not completely projective, and therefore also only gave the partial information whether you were in the up and down state. Okay? And then in between, we inserted the measurement along any direction. And these measurements along that certain direction, they would then be given, hopefully, by the equivalent to my lower formula and not to this upper formula, because I think this formula is right, while this is based on an assumption, of course, about the state at the time. So here is some of the states. This is just the rho prediction, where if you prepare an almost 91% polarized state here, then if you measure along rotated directions, then it becomes 50-50. If you rotate 90 degrees, it becomes quite opposite if you rotate 180 degrees, the qubit vector, spin vector. But now we do the retrodictive formula. So we actually populated the eigenstates. So this is the classical mixture interpretation. Then the retrodicted value in this experiment would be 1 as function of this rotation angle. That would be this dashed blue line. The retrodiction formula, I mean this past quantum state formula as I call it, that's the solid black line you see here. And the experiment is this green fuzzy thing that you see around here. So you see there's confirmation of the experiment of the formula, which I'm happy to see because it's a derived and correct formula, but it's a disproof of the state having been well described as just being in one of the Fock states at that time. That's also kind of funny, right? Because it worked so far, but I would not even use it. I would use it to guide my intuition, making statement of physical systems in the future. But I cannot really say that it's the same as the system being in that state, and me learning better where it was, because that's not what is happening here. It is more complicated than that. It's again going back to what we really do when we calculate probabilities in quantum mechanics. We calculate not probabilities for being in a state, but for being detected with that value. Okay, I'm going to conclude now. So just a summary, the state of a quantum system is conditioned on the outcome of probing measurements. This is a fantastic means to prepare very unusual states. You don't have to think about interactions. You should think about what can you do by measurement on, for example, two particles in terms of getting entanglement. And there's really many states that are much easier to make by measurement than to do by Hamiltonians. You can cool a quantum system by just measuring if it's in the ground state. And if it says, yes, I'm in the ground state, it is in the ground state, while a cooling apparatus may take forever to bring you in the ground state. And Leo DiCarlo is resetting qubits sometimes in his quantum computer by measuring them. If he measures that it's in the excited state, no problem, then he applies a pi rotation. So that's a unitary step. So you can actually do cooling by measurement and an easy feedback scheme. So that's really a wonderful tool. I cannot advertise it too much. Then this last thing was maybe not more on the semi-philosophical, but I'll show you Thursday that there's actually more to it than that, but also some very practical application that states in the past are now conditioned on the measurements until the present. When I by state mean the mathematics that allows me to give you probabilities for outcomes. But that's how I think of quantum mechanics states. It gives more certainty about certain quantities, and it begs new ideas. If you want to have a complementarity principle about past measurement or uncertainty relation for past measurements, then it's a new theory we have to develop, because these things are very much related to looking only forward in time. So with this, I thank you for your attention, and I hope you will be looking backward to at least the last part of the presentation. There's another mic here also.
Got this.
Okay, so, good.
Yeah. So thanks a lot for this. So I'm trying to understand this uncertainty relation bit. So usually when you're talking about the Heisenberg uncertainty relation, you are talking at it at a given time. There is a state at a given time, and there's an ensemble of that state. So for this retrodicted version, you are taking a single copy of that state and evolving it for later times, right? So is this the reason why there is a little bit of confusion, or do you?
I think I'm also only talking about measurements. I mean, the uncertainty is the uncertainty about the outcome of the measurement taking place at a definite time. And sometimes, or normally in quantum mechanics textbooks, you need to know the wave function at that time, right? And that is true. That wave function could actually be a function of the whole history, right? And in our, if you're probing continuously on the system, that wave function keeps evolving. So you have to know that process to know the wave function now, to make the prediction of the next measurement. So the uncertainty relation is given by the wave function now, but that wave function now is based on your knowledge on previous measurements. Because otherwise you wouldn't know what is the state, of course. And now I'm just saying that if you have the later measurements, then they will also tell you something. And they actually tell you, in the formalism, they tell you an object, which is also at the time of the measurement, this E thing, and those two together gives you the outcome. But let's not care so much about the mathematics. I'm talking about a measurement that is done at time t, using knowledge that I have. And if I want to guess the outcome, of course, I can also guess what you get at time t any moment later, because I can still use the wave function to calculate. If I know the wave function at time t, I know the outcome. But later, I also know more, because I also know the later measurements.
And maybe just a brief question about the signal-to-noise ratio in the retrodicted Harosh experiment. So the improvement in the signal-to-noise ratio, is this sort of, should I understand it as an amplification of the signal without noise, or should I sort of, or are you sort of correcting for the noise? How does, maybe this will, you'll go into it on Thursday more.
The story of signal-to-noise in the practical measurement is very much also related to what you could call the measurement strength. So of course, you can say, how much do I learn per nanosecond of probing or per microsecond of probing? And in the case of Harosh, there's a rate by which he's sending atoms through the cavity. And there's also a strength of the coupling of the atom to the field. So if I take that rate down, I will learn more slowly. And that will also give me fewer counts in a certain interval. And that will decrease my signal to noise in some sense in that experiment. And the same is true with the optical probing, where you're probing with homodyne detection. If you use a stronger laser field, then it's easier to measure the phase shift. So then you will also faster learn what is the phase shift. And that will also give you better signal to noise. So that's the same thing as your question. So it's often a parameter we can actually turn a little bit on and up and down, the measurement strength. And then, of course, you have to compare that to the other dynamics. So in our Roche experiment, you have to compare with the loss rate of photons out of the cavity. So if you want to have very clean, well-known Fock state, you have to measure much faster than the decay rate of photons out of the cavity. And then you can maintain knowledge that you have 4 photons in the cavity. But at some point it gives up, I lost it, and then you have only 3. And the question is that going to be a steep step down, or is it going to be a long step down? Well, that's if your measurement doesn't give you good measurement statistics on the time scale of gamma, then it will look like a longer interval, because you have to integrate the signal for so long that you are sure you're in the other state. And this is unavoidable. And the trajectories just do that for us, right? We can see that the state changes gradually and it will change gradually on a time scale, which is not the physical time scale of the jump. It's the typical, it's the time scale of us learning, and it's governed, just coming back to your question, exactly by the signal to noise in the measurement signal. Yeah.
Thank you for the nice talk. I was really confused by one statement you made, that the past quantum states are not affected by decoherence.
Yes. So that decoherence that happens when I'm probing on my system now is not acting as noise on the system in the past, right? If, for example, there's a spontaneous emission event happening in my atomic gas ensemble, that's not very good. That may heat up the ensemble, but it doesn't make it warmer in the past. The measurements I do can update my knowledge about things in the past. I mean, like the archaeologist, so the archaeologist is not going to, hitting down with a spade and he found out there were people living here 2,000 years ago. There's no risk he's going to kill any of them, right? Because they actually died 2,000 years ago. So you are not changing the physical state by the action of what you're doing, but you're changing your knowledge about the state of the system by the measurements you do. And these actions, like heating, they don't affect the past. They will affect the system going into the future.
Yes,
I might cut some bones, of course, but I don't cut the living person.
But in my head, the measurement record that you have already is affected by all the decoherence process that is happening continuously.
Yes, up to any moment in time, if all decoherence happening earlier has of course left a trace. You have broadened the distribution because you have been heated by all these processes. And you keep broadening and broadening into the future because you always do that. You heat up by all the measurements you do, but you're not heating the past state by that process.
It's because the graph that you showed of variance versus squeezing, it showed a drastic improvement, for example.
Yes. Oh, sorry, I switched it off. That was pessimistic of me, thinking there would be no questions. So let's see if I can just get back to this one. This is before the crazy part of the talk. Here it is. So we start going down, even in the forward direction, because squeezing is good, and it works, and it works, and it works. But then the process regrettably starts heating up the atomic ensemble. So now, from now on, you are actually, unfortunately, at the same time as you're learning something, there's a competition between you learning something and the state becoming broader for other reasons, for the heating reasons. So down here, it is also getting broader and broader. And actually, it's exactly the same data who produce that curve and that curve, except that on this curve, we try to predict the next measurement, next measurement, next measurement. On this curve, we try to retrodict what gave that measurement right here. So due to the measurements I have been doing all the way down to here, I'm asking, what was actually the outcome done at this earlier time? And the reason it's a better guess is because it's a different guess. Up here, I compared the outcome with a value I thought would be the good one. But based on the later measurement, I actually revised my view, and I thought it would be another value that was a good one. And fair enough, the scatter around that point was smaller. This retrodiction is efficient for a certain time, the coherence type of the system essentially. And then after that, you don't learn much more. This thing down here is a more spurious detail, but there's a huge error bar in this variance. In principle, you shouldn't get dumber by things you learn later. So in principle, you should not get worse at retrodicting the past by much later measurement. Then you should just stick with the minimum. But there's a consistency, at least with the error bars, that you go to a constant level down here.
So I didn't know, it is going up a little bit at...
Yeah, this is going up, but it's also very uncertain, as you can see. And the reason is that the ensemble is now really hot and noisy, and we cannot really trust. I mean, it's the theory who's also agreement with that, but this is not useful anymore to retrodict anything. Okay. Yeah. So if this is what you're talking about, thank you very much. This is not explained by what I said.
Thank you.
Yeah, I actually have two questions. It's so when you did this squeezing in the position and momentum, actually, can I think of this past quantum state as basically? It looks like it for me that you first do a measurement in position and then the approximate measurement in position and then a measurement in momentum.
Yes.
And the difference between the past quantum state and the retrodiction is that the experiment is changed by the fact that you measure in between the two positions.
Exactly. So I mean, in a fast explanation, you could describe this as an instantaneous thing squeezing P and an instantaneous thing squeezing X. course, that's not how it works in the experiment. It's a more dynamical theory, but it's exactly as you said, yeah.
Thank you very much for your nice talk. So I have a question about you talk about the application of the backward equation. I was wondering to know if it's useful to use it for feedback, for example. Or...
Yes, so that's a lovely question, and of course we discussed that also very early with Côte. And the problem is, if feedback is something you like to do to the state for it to become better, it's already too late because you're already in the future of that point. And of course, I cannot go back in time and do something better. So it has to be a little bit more advanced, but one thing I have in mind is that learning the past better also makes you learn better what are the drifts in the system. So I may learn that the system is actually not only being in a position, but that it is changing that position in some direction. And then, of course, if I know that velocity better, if I know the slope of that evolution better, then I can use that in a future feedback to correct for it. So it's a little bit like if you know I want to be in a particular place with my car and I measure the position with some error. But if I actually get to know the velocity very precisely, then of course that's what I really need to adjust my future state. So this idea that you could use maybe this to learn past the trends, and it could both be a trend in what the quantum system is doing, but it could actually also be if one of the physical parameters is changing. So then you could learn that there's a drift of a parameter in your experiment, and the best feedback you could do would not only be to adjust what you think is the value now, but to adjust what you think is going to be the value in the next interval unless I do nothing. And there, this trend would be useful. And then the knowledge about the past could be useful. I've not done this myself, so it's actually a speculation, right? But I think that would be how I could see this come in use. And maybe I will never be smart enough to do it, but we're also having a program with machine learning now, and maybe machine learning could actually take the record, and it could be fun to see if a machine learning agent could actually find an optimum feedback strategy who does exactly what you say, uses the full record and this kind of information. But at the end of the day, what you do now will only be conditioned on what you have learned until now. So in some sense, it becomes maybe a non-Markovian assessment of those data. But it will, of course, always be interpreted that my knowledge now is used to do the future step.
Yeah, hi, thanks for the nice talk. So I had two very short questions, and I hope I didn't misunderstand something. So at any given point T, if you're thinking in terms of quantum trajectories, there could have been several trajectories that could have ended you there.
Yes.
So in that case, how would the retrodiction work? Like there could have been several possible points that could have...
Yes, so thank you for the question. Actually, this is not the situation, you know. The situation is that I did do the earlier measurement and I have the state condition on those earlier measurements. And I also do have the later measurement. So I also have that E matrix. You are right that other experiments could have led to the same values, but that's not so much what I'm guessing about. I'm not asking about whether that earlier record could have been something else, because I already know what it is, and the same with the later one. So there's actually only this point in the middle, which I'm questioning what's the probability for that. And there you're of course right. There are all possibilities at place, and there's actually also probabilities for all of them. But otherwise it's a good question. And there were actually early experiments, that's before I met Côte, where at Berkeley, they wanted to validate that the trajectory description is right, the normal trajectory description. And of course the trajectory gives a prediction for the outcome of a measurement. But when you do a measurement, you get a random outcome. So how will you ever validate that 60% excitation probability is the right number if you only do one experiment and you get that it's excited? So they actually wanted to have that 60% appear in many trajectories, such that they took a whole collection of trajectories who all said 60%, and then they checked the average outcome of measurement on that ensemble of histories is also giving 60%. And then they confirmed that, and that is in the line with what you just asked.
Yeah, and the second question is, how does this reconcile with non-Markovian dynamics? I mean, because...
I think it reconciles very bad with non-Markovian dynamics. I mean, non-Markovian dynamics is a state where the time evolution depends on the state in the past. Very often, actually, in a more complicated way, it depends on the state of the system and its environment, because that's where the memory is often stored. So that's very complicated. So first of all, I don't have a Markovian master equation, but sometimes we get something called a time convolutionless master equation, which is a thing with time-dependent coefficients. That's an approximation which works for evolving the density matrix forward, but it doesn't capture the correct correlations with the bath. So I think that I would not dare just write down those equations for rho and E and apply them. I mean, and even the quantum jumps, I would say we don't have a good trajectory situation for when you do measurements on non-Markovian dynamics, right? I mean, there are ansatses, there's ideas by Jyrki Pilo in Finland, a kind of jump approach, which does what I also wanted to do in the beginning. He can make quantum wave function dynamics stochastic, which reproduces the time convolutionless non-Markovian master equation. But that does no longer correspond to a measurement process. So he's not doing a trajectory of measurement condition dynamics. He's doing a simulated wave function approach to density matrix theory. So I don't think we have a theory of measurement which is good in connection with non-Markovian. Let me talk about the physics too, because if you have an atom who scatters a photon inside a cavity, then there's a chance it may reabsorb the photon again. So if you look at the atomic dynamics, it's non-Markovian, because it can be re-excited by the excitation it had itself earlier on. But of course, you can put a detector outside the cavity. So I can actually solve this dynamics. I just have to solve for the two systems together. If I have a click outside this cavity, I know when the cavity lost the photon, but I don't know what happened to the atom at which point. So I cannot infer the atomic dynamics from the photon I see far away. You could also have a photon propagating through a dispersive medium, so different frequency components have different velocity. That would be characteristic of non-Markovian reservoir. And that means when I get a click, I actually don't know when the atom decayed, because if it was the red tail of the frequency spectrum I saw, then it has propagated with one speed, but if it's in the blue tail, then there's another time that it actually had to decay to give me that photon. So I cannot do a collapse on the atomic state according to seeing such a photon in such a non-Markovian setting. So I find it both conceptually but also physically difficult to make the theory, but maybe mathematically we can do it. And again, maybe this AI thing can learn how to do it and also find out what the good jumps to stick into such a formalism. There are people working on this, of course, and I mean, we're looking anxiously what can be done.
Now we break for coffee, tea.